In this video, we're going to look at the reduction of carbonyl compounds to form alcohols. So we're going to kind of group our carbonyl compounds together based on the different type of reactions that we can get and reagents that we need. But first, let's remember what reduction is. And reduction in organic chemistry means either we are losing bonds to oxygen or adding bonds to hydrogen. So if we think about this in a generic sense with respect to a carbonyl, this is the common, just generic symbol for reduction. What we're going to get is we do lose a bond to oxygen. So we're going from double bond to single bond. That becomes an alcohol. And we also add a bond to a hydrogen that wasn't there before. So this is the general overall reaction. The type of alcohol that you get, primary, secondary, or tertiary, depends on what you start with. So again, we're going to group our carbonyls together based on that. So first, let's look at aldehydes and ketones. So aldehydes are where we have an R group on one side of the carbonyl and a hydrogen on the other side. If we do a reduction of the aldehyde, we'll talk about specific reagents here in a minute, what you're going to end up with is a primary alcohol. All right. So what's happening, we have that R group. We're making the carbonyl oxygen the alcohol. There was already a hydrogen there, and now I'm going to add a second hydrogen. So primary because it's attached to only one other carbon. If I look at a ketone has two R groups, one on either side of the carbonyl. So if I do a reduction here, what I'm going to end up with is a secondary alcohol. So now those two R groups that were on the original structure are still there. I convert the oxygen to the alcohol group, and I'm adding one hydrogen. So we've got two different reagents we can use here. One is sodium borohydride, typically used with ethanol, and then followed up with acidic workup, so an acid. This is a pretty safe reagent to use, very commonly used. Another option is to use lithium aluminum hydride, also an ether. Oh, sorry, this is an ether, not alcohol. That would be bad. So lithium aluminum hydride and ether, and then also has an acid workup to follow up at the end. This reacts very violently if it comes into contact with water. So it's kind of avoided in the lab if at all possible. And it's also explosive if it gets over 120 degrees Celsius. So temperature issues, water issues, all reasons to try to avoid using it in lab if at all possible. And that's why the sodium borohydride is more common. But here, either of them work on paper, so either of them would be acceptable answers. So let's look at a specific example. We're going to start with an aldehyde. And I'm going to react it with sodium borohydride. So remember, an aldehyde with the sodium borohydride reduction is going to convert to a primary alcohol. So what you need to do here is just make sure you have the right carbon groups coming along. So I've got 3 carbons. That third carbon is then attached to the O. That becomes the alcohol group. The hydrogen is still there. And then what I am adding is now a second hydrogen. So there is the alcohol that forms. If you want to write it a little more cleanly, we've got 3 carbons, the alcohol. Propanol is actually what we have here. Okay. Another example, if we look at a ketone, this time let's use the lithium aluminum hydride. Again, make sure you have the proper carbon chains. We have 1, 2, 3, 4, 5, 6. We have a methyl group coming off of that third carbon. The oxygen is coming off of the fourth, and that becomes the alcohol. Again, you are also adding a hydrogen. It doesn't have to be shown in line angle, but it's fine to show it if you wish. One thing you do want to keep in mind is the possibility for chiral centers and therefore forming enantiomers or diastereomers. If we look back at the aldehyde example, you're forming a primary alcohol, and a primary alcohol is always going to have those two hydrogens attached to that carbon, and therefore it's never going to be chiral. So you don't have to worry about it there. However, with ketones, you're going to form a secondary alcohol. And here, if the R groups on either side are different, you are going to form a chiral center. So you can tell just by looking at the starting ketone, I do have two different R groups on either side. So I've got those two groups plus the alcohol plus the hydrogen. That's four different groups attached to a carbon. So we do have a chiral center. So to be fully accurate here, we're going to show both enantiomers, alcohol forward, alcohol backward. Those are the two products that are formed. And what you get is a racemic mixture, 1-to-1 ratio of each. One is not preferred over the other. The next set of carbonyls that we're going to look at is the carboxylic acids and esters. So carboxylic acids and esters, our carboxylic acid, we have an R group on one side of the carbonyl, an OH group on the other. Ester, we have an R group on one side, oxygen with another R group on the other side. So either of these, if we do a reduction, what we're going to end up with is a primary alcohol. So what happens is the R group, meaning the R group here in the carboxylic acid, or the R group that is on the side of the ester without the oxygen, that stays as part of the alcohol. You get your OH, and you're actually going to be adding then two hydrogens. This reaction kind of goes through a two-step process to get here. So the R that is attached to the oxygen in the ester, that goes away. All right, you get a byproduct of a different substance whenever you have actually another alcohol. So you would get HOR prime as well, but that's typically not the alcohol that you're aiming to produce. It's typically focused on the other side of the carbonyl. So reagents here, we have the same two, the sodium borohydride and the lithium aluminum hydride. The sodium borohydride works slowly on the esters. And then there's no reaction for the carboxylic acids. Lithium aluminum hydride is going to work for everything. So here's an example where if you're trying to do a reduction of a carboxylic acid, you're going to have to go with the more dangerous lithium aluminum hydride if doing this in the lab, because the sodium borohydride doesn't work. So let's look at a few examples here. So notice in this example, we actually have two functional groups. We have a carboxylic acid as well as an ester. So when you've got multiple functional groups, you need to look at both of them and also kind of think about them separately. Sorry. So if we think about carboxylic acid with sodium borohydride, we just said that sodium borohydride is not strong enough to work with the carboxylic acid. So there's going to be no reaction or no change on that part of the molecule. For an ester, we said it's slow, but that it does happen. And what it's going to convert to is a primary alcohol. So when I'm thinking about my product, the carboxylic acid stays. It does not change. Then the carbon that had the carbonyl for the ester is going to turn into the alcohol, and it's going to turn into a primary alcohol. So the other two bonds there are to hydrogen. So if I clean this up, here is the product that forms. One more example. This time we're going to look at a cyclic ester and think about how this is going to turn out. This time we're going to react it with lithium aluminum hydride. So again, we need to think about our groups separately because I do have two. I have an ester and I have a carboxylic acid. Lithium aluminum hydride works for both of them. So the carboxylic acid, it's going to convert to a primary alcohol. Ester is also going to convert to a primary alcohol. Here, before I said we kind of lose the other R group of an ester, but here that other half of the molecule is still attached, so it doesn't totally disappear. It's going to stick around. So we are going to break this bond. Okay, and before, if that piece was off by itself, it would float away, separate product, but here it's attached. So we're going to have 1, 2, 3, 4, 5 carbons. That first carbon that I had is going to become a primary alcohol. Third carbon over was the carboxylic acid, so it's going to become a primary alcohol. And then the fifth carbon is also attached to an oxygen, and that's the other half of the ester, and we said that also turns into an alcohol. So here's the final product. So this one was kind of a little bit of a challenge problem here where both functional groups, both are reacting. Because it's a cyclic ester, we don't lose the other half of the molecule. It actually stays part of our product.